Welcome to our exploration of electromagnetic wave propagation. Electromagnetic waves are fundamental to our modern world, enabling everything from radio broadcasts to wireless internet. But how do these waves actually travel through space? In this video, we'll break down the science behind electromagnetic wave propagation, starting with the basics and moving into more complex concepts. Whether you're a student, a science enthusiast, or just curious about the invisible forces all around us, this journey will help you understand how energy moves without the need for wires or even a physical medium. Let's begin by understanding what electromagnetic waves are and why their propagation is so important. Electromagnetic waves are oscillations of electric and magnetic fields that travel through space. Unlike sound waves, which need air or another medium, electromagnetic waves can move through a vacuum. This unique property allows them to travel from the sun to Earth, bringing us light and warmth. The two fields, electric and magnetic, are always perpendicular to each other and to the direction the wave is moving. This interplay is what makes electromagnetic waves so fascinating and versatile. Next, let's look at the different types of electromagnetic waves and where we encounter them in daily life. Electromagnetic spectrum includes a wide variety of waves, from radio waves and microwaves to visible light, ultraviolet, X-rays, and gamma rays. Each type of wave has a different wavelength and frequency, which determines its energy and how it interacts with matter. For example, radio waves are used for communication, while X-rays help doctors see inside the body. Visible light is the small part of the spectrum that our eyes can detect. Understanding these types helps us appreciate the many ways electromagnetic waves impact our lives. Now let's explore how these waves are generated. Electromagnetic waves are produced whenever charged particles like electrons accelerate. This can happen in many ways, such as when an antenna transmits a radio signal or when electrons jump between energy levels in atoms, emitting light. The changing electric field creates a changing magnetic field and vice versa, allowing the wave to sustain itself and move forward. This self-propagating nature is what enables electromagnetic waves to travel vast distances, even across the vacuum of space. Next, we'll see how these waves move through different environments. One of the most remarkable features of electromagnetic waves is their ability to travel through a vacuum. Unlike sound, which needs air, electromagnetic waves don't require any material to move. In a vacuum, these waves travel at the speed of light, about 299,792 kilometers per second. This is why sunlight reaches us from the sun, even though space is nearly empty. The absence of obstacles means the waves can travel long distances without losing much energy. Let's now look at what happens when electromagnetic waves encounter different materials. When electromagnetic waves pass through materials like glass, water, or air, their speed and direction can change. This is due to interactions with the atoms and molecules in the material. For example, light slows down when it enters water, causing it to bend, a phenomenon known as refraction. Some materials absorb certain wavelengths while others let them pass through. Understanding how waves interact with different substances is crucial for designing technologies like fiber optics and wireless communication systems. Next, we'll discuss the concept of wave reflection. Reflection occurs when electromagnetic waves hit a surface and bounce back. This is why you can see yourself in a mirror. The light waves reflect off the glass. Reflection is also essential in technologies like radar, where waves bounce off objects to detect their position. The angle at which the wave hits the surface determines the angle at which it reflects, following the law of reflection. This principle is used in countless applications, from satellite dishes to optical instruments. Now let's move on to another important phenomenon, refraction. Refraction is the bending of electromagnetic waves as they pass from one material into another with a different density. This is why a straw looks bent when placed in a glass of water. The change in speed as the wave enters a new medium causes it to change direction. Refraction is crucial in lenses, which focus light to form images in cameras, glasses, and telescopes. By understanding refraction, scientists and engineers can design better optical devices and communication systems. Next, let's talk about diffraction and how waves can bend around obstacles. Diffraction occurs when electromagnetic waves encounter an obstacle or opening and bend around it. This is why you can hear someone speaking even if they're around a corner. The sound waves diffract. Similarly, light and other electromagnetic waves can spread out after passing through a small slit or around an edge. Diffraction is important in technologies like radio broadcasting, where waves must navigate buildings and terrain. Understanding diffraction helps engineers design better antennas and communication networks. Next, we'll explore what happens when waves overlap, interference. When two or more electromagnetic waves meet, they can interfere with each other. This interference can be constructive, where the waves add together to make a stronger signal, or destructive, where they cancel each other out. Interference patterns are seen in everyday life, such as the colorful patterns on soap bubbles or oil slicks. In technology, interference can affect wireless signals, sometimes causing dropped calls or slow internet. By understanding interference, engineers can design systems to minimize unwanted effects. Next, let's look at polarization. Polarization refers to the orientation of the electric field in an electromagnetic wave. Light from the sun is unpolarized, meaning the electric field vibrates in all directions. However, certain filters or surfaces can polarize light, allowing only waves with a specific orientation to pass through. Polarized sunglasses use this principle to reduce glare from surfaces like water or roads. Polarization is also important in communication systems, where it helps separate signals and reduce interference. Next, let's discuss the speed of electromagnetic waves. In a vacuum, all electromagnetic waves travel at the same speed. the speed of light. However, when these waves move through materials like glass or water, they slow down. The amount of slowing depends on the material's properties. This change in speed is why light bends when entering water. The speed of electromagnetic waves is a fundamental constant in physics and is used in calculations ranging from GPS navigation to astronomy. Next, let's look at how energy is carried by electromagnetic waves. Electromagnetic waves carry energy as they travel. The amount of energy depends on the wave's frequency and amplitude. Higher frequency waves like X-rays and gamma rays carry more energy than lower frequency waves such as radio waves. This energy can be absorbed by materials, causing effects like heating or even chemical changes. For example, microwaves heat food by causing water molecules to vibrate. Understanding how energy is transferred by electromagnetic waves is key to many technologies. Next, let's discuss the concept of wave attenuation. As electromagnetic waves travel through a medium, they gradually lose energy, a process called attenuation. This can happen due to absorption, scattering, or reflection. For instance, radio signals weaken as they pass through walls or the atmosphere. Attenuation limits the range of wireless communication and is a key factor in designing networks and devices. Engineers use various techniques to reduce attenuation, such as amplifiers and repeaters. Next, let's explore the concept of wavelength and its importance. Wavelength is the distance between two consecutive peaks of an electromagnetic wave. It determines the wave's energy and how it interacts with matter. Longer wavelengths like radio waves can travel farther and penetrate obstacles more easily. Shorter wavelengths like ultraviolet or X-rays carry more energy but are absorbed more quickly. Wavelength is a crucial parameter in designing antennas, sensors, and optical devices. Next, let's discuss frequency and its relationship to wavelength. Frequency is the number of wave cycles that pass a point per second. It's measured in Hz Hz. Frequency and wavelength are inversely related. As one increases, the other decreases. High-frequency waves like X-rays have short wavelengths and high energy. Low-frequency waves like radio waves have long wavelengths and lower energy. Frequency is a key factor in communication systems, determining how information is transmitted and received. Next, let's look at amplitude and its significance. Amplitude is the height of the wave from its central axis to its peak. It represents the strength or intensity of the electromagnetic wave. Higher amplitude means more energy is carried by the wave. In radio transmissions, amplitude can be varied to encode information, a technique known as amplitude modulation (AM). Amplitude also affects how waves interact with materials, such as how bright a light appears. Next, let's discuss the concept of phase in electromagnetic waves. Phase describes the position of a point within a wave cycle. When two waves have the same phase, their peaks and troughs align, leading to constructive interference. If they are out of phase, they can cancel each other out. Phase is important in technologies like phased array antennas, which use multiple signals to steer beams of electromagnetic waves. By controlling phase, engineers can enhance signal strength and direction. Next, let's look at the concept of coherence. Coherence refers to how well the phases of two or more electromagnetic waves match over time. Coherent waves maintain a constant phase relationship, which is essential in applications like lasers and holography. Incoherent waves, on the other hand, have random phase relationships and do not combine in a predictable way. Coherence is crucial for producing sharp, focused beams of light and for technologies that rely on precise wave interactions. Next, let's discuss the electromagnetic spectrum in more detail. Electromagnetic spectrum is the full range of all possible electromagnetic wave frequencies. It includes radio waves, microwaves, infrared visible light, ultraviolet, X-rays, and gamma rays. Each region of the spectrum has unique properties and uses. For example, microwaves are used in cooking and communication, while ultraviolet light is used for sterilization. Understanding the spectrum helps us harness electromagnetic waves for countless applications. Next, let's look at how antennas transmit and receive these waves. Antennas are devices that transmit and receive electromagnetic waves. When an electric current flows through an antenna, it creates oscillating electric and magnetic fields, launching electromagnetic waves into the air. Receiving antennas capture these waves and convert them back into electrical signals. Antennas are used in everything from radios and televisions to cell phones and satellites. Their design depends on the wavelength and frequency of the waves they handle. Next, let's discuss waveguides and their role in guiding electromagnetic waves. Waveguides are structures that direct electromagnetic waves along a specific path. They are commonly used for microwaves and higher frequency signals. Waveguides can be made from metal tubes or optical fibers, depending on the type of wave. By confining the wave, waveguides minimize energy loss and interference. This technology is essential in radar systems, satellite communications, and fiber optic networks. Next, let's explore the concept of resonance in electromagnetic system. Resonance occurs when an electromagnetic system naturally oscillates at a specific frequency. When waves of that frequency are applied, the system absorbs energy efficiently, leading to large oscillations. Resonance is used in radio tuners, where you select a station by matching the tuner's frequency to the broadcast signal. It's also important in lasers and other devices that rely on precise frequency control. Next, let's discuss the concept of bandwidth and its significance in communication. Bandwidth refers to the range of frequencies that a communication channel can transmit. Wider bandwidth allows more information to be sent in a given time. For example, high-speed internet uses channels with large bandwidths to deliver fast data. Bandwidth is a key factor in designing wireless networks, radio stations, and television broadcasts. Managing bandwidth efficiently ensures clear signals and reduces interference. Next, let's look at the concept of modulation in electromagnetic communication. Modulation is the process of varying a property of an electromagnetic wave to encode information. Common techniques include amplitude modulation (AM), frequency modulation (FM), and phase modulation (PM). Modulation allows multiple signals to share the same channel without interference. It's used in radio, television, and digital communication systems. By choosing the right modulation method, engineers can optimize signal quality and data rates. Next, let's discuss the role of noise in electromagnetic propagation. Noise refers to unwanted signals that interfere with the transmission and reception of electromagnetic waves. Sources of noise include natural phenomena like lightning and man-made devices like motors. Noise can distort signals, reduce clarity, and limit communication range. Engineers use filters, shielding, and error correction to minimize noise and improve reliability. Understanding noise is essential for designing robust communication systems. Next, let's explore the concept of signal-to-noise ratio. Signal-to-noise ratio (SNR) measures the strength of the desired signal compared to background noise. A higher SNR means a clearer, more reliable signal. SNR is crucial in wireless communication, audio systems, and data transmission. Engineers strive to maximize SNR by boosting signal strength and reducing noise. This ensures that information is transmitted accurately and efficiently. Next, let's discuss the concept of multiplexing in communication system. Multiplexing is a technique that allows multiple signals to share the same communication channel. This is done by combining signals in different ways, such as time division, frequency division, or codivision multiplexing. Multiplexing increases the efficiency of communication networks, allowing more users and data to be transmitted simultaneously. It's used in telephone networks, internet connections, and satellite communications. Next, let's look at the concept of propagation mode. Electromagnetic waves can travel in different modes, depending on the environment and frequency. Common modes include ground wave, sky wave, and line-of-sight propagation. Ground waves follow the Earth's surface, sky waves bounce off the ionosphere, and line-of-sight waves travel directly between antennas. Each mode has advantages and limitations, affecting range and signal quality. Understanding propagation modes is essential for designing effective communication systems. Next, let's discuss the impact of the atmosphere on wave propagation. Earth's atmosphere can affect the propagation of electromagnetic waves in many ways. Factors like humidity, temperature, and atmospheric layers can bend, scatter, or absorb waves. For example, radio signals may travel farther at night due to changes in the ionosphere. Weather conditions can also impact signal strength and clarity. Understanding atmospheric effects helps engineers predict and optimize communication performance. Next, let's look at the concept of fading in wireless signals. Fading is the variation in signal strength as electromagnetic waves travel through the environment. It can be caused by obstacles, reflections, and atmospheric conditions. Fading can lead to dropped calls or slow data rates in wireless networks. Engineers use techniques like diversity reception and error correction to combat fading and maintain reliable communication. Understanding fading is crucial for designing robust wireless systems. Next, let's discuss the concept of path loss. Path loss is the reduction in power density of an electromagnetic wave as it travels through space. It increases with distance and can be affected by obstacles, terrain, and atmospheric conditions. Path loss is a key factor in determining the range of wireless communication systems. Engineers use mathematical models to predict and compensate for path loss, ensuring strong signals over long distances. Next, let's look at the concept of free space propagation. Free space propagation describes how electromagnetic waves travel in an unobstructed environment, such as outer space or open air. In free space, waves spread out uniformly in all directions and their strength decreases with distance. This model is used to predict signal behavior in satellite communications and deep space missions. Free space propagation is the simplest case, but real-world environments often introduce additional complexity. Next, let's discuss the concept of multipath propagation. Multipath propagation occurs when electromagnetic waves take multiple paths to reach the receiver, often due to reflections off buildings, terrain, or other obstacles. This can cause signals to arrive at different times, leading to interference and signal distortion. Multipath effects are common in urban environments and can impact wireless communication quality. Engineers use techniques like equalization and diversity to mitigate multipath issues. Next, let's look at the concept of absorption in materials. Electromagnetic waves pass through materials, some of their energy is absorbed by the atoms and molecules. This absorption can convert wave energy into heat or cause other effects like fluorescence. Different materials absorb different wavelengths to varying degrees. For example, glass is transparent to visible light but absorbs ultraviolet rays. Understanding absorption is important for designing buildings, windows, and protective coatings. Next, let's discuss the concept of scattering. Scattering occurs when electromagnetic waves encounter small particles or irregularities in a material, causing the wave to change direction. This is why the sky appears blue. Shorter wavelengths of sunlight are scattered by air molecules. Scattering can reduce signal strength and clarity in communication systems, especially in fog, rain, or dust. Engineers must account for scattering when designing wireless networks and optical systems. Next, let's look at the concept of reflection loss. Reflection loss refers to the reduction in signal strength when electromagnetic waves reflect off surfaces. Some energy is always lost during reflection, depending on the material and angle. This loss can impact the efficiency of antennas, mirrors, and other devices. Engineers use coatings and special materials to minimize reflection loss and maximize signal transmission. Next, let's discuss the concept of transmission windows in material. Transmission windows are specific wavelength ranges where materials allow electromagnetic waves to pass through with minimal absorption or reflection. For example, glass has a transmission window in the visible spectrum, making it transparent to our eyes. These windows are important in designing optical fibers, sensors, and imaging devices. By choosing the right materials, engineers can optimize the performance of communication and sensing systems. Next, let's look at the concept of guided wave propagation. Guided wave propagation occurs when electromagnetic waves are confined to a specific path, such as in cables or optical fibers. This allows signals to travel long distances with minimal loss and interference. Guided waves are essential for high-speed internet, cable television, and secure communications. The design of the guide, its shape, size, and material affects how well it transmits signals. Next, let's discuss the concept of surface wave. Surface waves travel along the boundary between two different media, such as the ground and the air. These waves are important for long-distance radio communication, especially at low frequencies. Surface waves can follow the curvature of the Earth, making them useful for broadcasting over large areas. However, their strength decreases with distance and ground connectivity. Understanding surface wave propagation helps engineers design effective communication systems for remote location. Next, let's look at the concept of space waves. Space waves travel directly through the atmosphere, usually in a straight line between transmitting and receiving antennas. These waves are used for television, FM radio, and satellite communication. Space wave propagation is limited by the horizon, so antennas must be placed high enough to maintain line of sight. Obstacles like buildings or mountains can block space waves, requiring repeaters or relay stations. Next, let's discuss the concept of ionospheric propagation. Ionospheric propagation occurs when electromagnetic waves are reflected or refracted by the ionosphere, a layer of charged particles high above the Earth. This allows radio signals to travel beyond the horizon, making long-distance communication possible. The ionosphere's properties change with time of day, season, and solar activity, affecting signal quality. Understanding ionospheric propagation is essential for amateur radio, aviation, and global broadcasting. Next, let's look at the concept of tropospheric propagation. Tropospheric propagation involves the bending or scattering of electromagnetic waves in the lowest layer of the atmosphere, the troposphere. Weather conditions like temperature inversions and humidity can cause waves to travel farther than usual. This effect is important for VHF and UHF radio, television, and radar systems. Tropospheric propagation can lead to unexpected signal reception over long distances, especially during certain weather patterns. Next, let's discuss the concept of fatting and diversity techniques. Diversity techniques are used to improve the reliability of electromagnetic wave reception. By using multiple antennas or different frequencies, engineers can reduce the impact of fatting, interference, and other signal issues. Diversity is especially important in wireless communication, where signals can be affected by obstacles and environmental changes. Techniques include spatial diversity, frequency diversity, and polarization diversity. Next, let's summarize what we've learned about electromagnetic wave propagation. We've covered the fascinating journey of electromagnetic waves, from their generation and propagation to the many factors that influence their travel. Understanding electromagnetic wave propagation is essential for modern technology, from communication networks to medical imaging. By mastering concepts like reflection, refraction, interference, and attenuation, engineers and scientists can design better systems for our connected world. We hope this video has given you a clear and engaging overview of how electromagnetic waves move and why they matter in everyday life.